To understand the photoelectric effect, we first need to understand the metal itself. Inside a metal, electrons move freely, like a gas of charged particles. But they are trapped. To escape the surface, an electron needs a specific amount of energy. Not too much, just enough to break the bonds that hold it in. This minimum energy is called the work function, represented by the Greek letter phi. It varies from metal to metal. For some it's small, electrons escape easily. For others, hold tight. No electron can escape without at least this much energy. Now a photon arrives. It carries energy equal to h times f. If that energy is less than the work function, the electron absorbs it but cannot escape. It vibrates, heats up, but stays inside the metal. The photon is wasted. This is the first key insight. Below a certain frequency, the threshold frequency, no single photon carries enough energy. Below the threshold frequency, no single photon has enough energy. The electron absorbs them one by one, but each is too weak. It shakes and vibrates, but never breaks free. Red light, no matter how bright, cannot do the job. For most metals, this threshold lies in the ultraviolet, which is why blue and violet light work, but red does not. The kinetic energy of the escaping electron depends only on the frequency of the light. Higher frequency means more leftover energy. The electron moves faster. This is Einstein's prediction, and it defied classical physics completely. Above the threshold, something different happens. The foe delivers more than enough energy. The electron uses some to escape, the work function, and keeps the rest as kinetic energy. It flies out of the metal. This is the photoelectric effect. Classical wave theory said, more intensity, more energy. Einstein said, more intensity, more electrons, but each electron gets the same energy. Until the prediction, this was what experiments would test. Intensity controls the number of photoelectrons. Frequency controls their speed. This was the prediction. This was what experiments would test. This is Einstein's photoelectric equation. Ke max equals hf minus phi. Photon energy minus work function equals electron kinetic energy. Simple, elegant, and utterly revolutionary. Einstein's equation predicts a straight line. The threshold frequency is where the line hits zero. The slope of that line is Planck's constant. And the point where the line would hit the y-axis extended gives the work function. Robert Millikan was one of the finest experimental physicists of his age. He did not believe in photons. He thought Einstein's idea was nonsense. He set out to prove it wrong. He spent 10 years perfecting his apparatus, determined to show that the photoelectric effect followed classical wave theory. Right? The waves do not right? The slope of that line is h, Planck's constant. The data lined up perfectly with Einstein, not with him. Millikan had proven his own beliefs wrong. The wave theory is sound. This will prove it. Adjusting the frequency now, recording the emissions. The data is inconsistent. This can't be right. The quantum effect is real? He failed. 10 years of work, the most precise measurements of his career, and the data lined up perfectly with Einstein, not with him. The slope of the line gave him Planck's constant, the same constant from black body radiation. The constant that was supposed to be just a trick. Millikan had proven his own beliefs wrong. Millikan published his results. He gave Einstein credit, but he never fully accepted the photon. He wrote that Einstein's equation worked. But he still believed light was a wave. He could not let go of the old world. The new one was too strange. In 1921, Albert Einstein received the Nobel Prize, not for relativity, for the photoelectric effect. Planck himself was there. He applauded the man who proved him right. Planck's constant was no longer a trick. It was the bridge between waves and particles, the conversion factor between frequency and energy, the quantum of action itself. The photoelectric effect proved light was quantized. But what about matter? What about the atom? If energy comes in packets, shouldn't electrons behave the same way? The answer would come from a young Danish physicist, Niels Bohr, and it would reveal a world stranger than anyone had imagined.